discrete time sinusoids. Okay, we are going to be looking at the sinusoids of the form x of n equal to a times the representation sine omega naught n plus phi. Omega naught is in radians, or you can look at a times cosine omega naught n plus phi. Okay. The first thing that we note down compared to continuous time signals. So, x of t is equal to a sine omega t omega naught t plus theta. Okay, if you look at a continuous time signal, if you look at omega naught, it starts from 0 and then goes all the way to infinity, 0 to infinity. So, basically you can get sinusoids of low frequency, high frequency. Low frequencies are in this region, this is low frequency, and high frequency are as your frequency approaches infinity. That is what we classify as the high frequency. Now, let us look at the representation of the discrete time sinusoids and derive the first important and a fundamental difference. Supposing you look at a frequency omega 1 that is equal to omega naught plus 2 pi times k. Okay, that means it is shifted by a multiple of 2 pi, shifted or increased by a multiple of 2 pi, multiple of 2 pi. Okay, write that down. So, we now are looking at a cosine omega 1 n plus phi, omega 1 n plus phi. Okay, omega n plus phi. Now, this is obviously a higher frequency than omega naught because you have added a multiple of 2 pi, but write it down. So, this is the same as cosine of omega naught plus 2 pi k multiplied by n plus phi. This is the same as a cosine omega naught n plus 2 pi k n plus phi. Okay, cosine of 2 pi plus theta, any multiple shifted by 2 pi plus theta will be the same angle. So, this is nothing but a cosine omega naught n plus phi. Very, very interesting. If you shift the frequency by a multiple of 2 pi, then you will get back the original frequency. That is, the behavior will be the same. So, omega 1 for all values of k, k 1, 2, 3, 4, all of them behave the same as omega naught. Okay. So, what we find in discrete time sinusoids is a important property which we capture as periodicity in frequency. Okay, very, very interesting, because we say that this is, why is it interesting? Because in continuous time there is no periodicity in frequency, there is periodicity in time, but there is no periodicity in frequency because frequency goes from 0 to infinity. Whereas for continuous, for discrete time, what we find is that there is a fundamental in periodicity that is present in frequency. Now, we need to study this in a little bit more detail, and therefore, I would like you to look at this particular illustration. These are discrete time illustration. Okay, this is a discrete time sinusoid. So, these are discrete time sinusoids. Start with omega equal to 0. Okay. So, a cosine omega naught n plus phi. If omega naught is equal to 0, you get cosine of 0 is equal to 1. So, therefore, you see all the samples are equal to 1. So, this corresponds to omega naught equal to 0. take a higher frequency, omega naught is equal to pi by 8. You have increased the frequency by a little bit. You see that now you can see the sinusoidal waveform. You can see that it is, you get samples which are positive, samples which are negative, and then you can see the signal showing some periodic behavior. Increase the frequency a little bit more, omega equal to pi by 4. You will see that the number of cycles has increased, so which means our understanding is that the frequency has increased. Now go all the way to omega naught equal to pi. Then what do you get? A cos omega naught n plus phi. So if omega naught is equal to pi, then it is cos pi n. So you have cos pi, cos 2 pi, cos 3 pi, cos 4 pi. Basically, you will get plus minus 1s. So this is sort of the frequency is changing very fast. Every sample is the changing polarity. So basically, this is also this. So this is a high frequency. You will agree. Okay, this is low frequency. High frequency, low frequency. Okay, we have gone from high frequency, you can say, draw the arrow all the way down here to high frequency. So from 0 to pi. Now look at a frequency which is 7 pi by 4. 7 pi by 4, is it greater than pi or less than pi? This is equal to 1.75 pi. So therefore, this is greater than, so this is greater than omega equal to pi. Higher frequency, but you plot it. What do you get? Exactly the same as what you got for pi by 4, as if the frequency is reducing. You increase it even further, omega naught equal to 15 pi by 8. It reduces even further, and then finally you go to 2 pi flat. So what we see is that if you plot the value of the rate of oscillations, okay, rate of oscillations, okay, you start from 0 and you go all the way to pi, you see that the discrete time sinusoids, the rate of oscillations increase from 0 to pi. Then from pi to 2 pi, very interesting behavior, it decreases and decreases all the way down to 0. Then beyond 2 pi, you will find that it increases and up to 3 pi, and then it decreases down to 4 pi. Again, this is a very unique behavior that is present in discrete time sinusoids. Okay, so what can we write down as the first observation? Observation number 1 about discrete time sinusoids is that discrete time sinusoids show a behavior that is periodic in frequency. Discrete sinusoids are periodic in frequency. Okay, very, very important. Not periodic in time. We have not said anything about periodicity in time. Only we talked about periodicity in frequency. Are periodic in frequency. Now, when you say that a function is periodic, you must tell what the period is. The period is equal to 2 pi. Any multiple of 2 pi will also satisfy. The period is equal to 2 pi or any multiple. Any multiple of 2 pi. Okay, so this is important for you to keep in mind. Now comes a very interesting observation. Okay, now let us look at the time aspect, time behavior of discrete time sinusoids. Discrete time sinusoids. Okay, now in continuous time, all sinusoids are periodic. All sinusoids are periodic. Right? You can see the periodicity that is present, are periodic. And period is nicely defined, that the period t is equal to 2 pi by omega. Okay, so basically this is the representation of the 2 pi by omega naught. So what we look at is all sinusoids are periodic regardless of the. So now come to the aspect of the discrete time. Discrete time. Discrete time, we have a sinusoid of the form a cosine omega naught n plus phi. Okay. Now supposing the signal is periodic. Okay, if periodic with period equal to n, some uppercase n, with period equal to n, then what this means is that a cosine omega naught n plus any multiple of n plus kn, k is an integer multiple of n, plus phi must be equal to a cos omega naught n plus phi. Okay, what do we mean by that? This is nothing but x of n plus kn. Okay, basically you have shifted it by an integer multiple of the period. This must be equal to x of n. Okay. Now, when we look at it in terms of the sinusoids, then what we are saying is that the period that you have omega naught kn, omega naught kn, if omega naught kn is equal to a multiple of 2 pi, if omega naught kn is equal to a multiple of 2 pi. So, at a minimum k, at least k equal to 1, if you say omega naught n must be equal to a multiple of 2 pi, multiple of 2 pi. Okay. So, what does that mean? It means that omega naught n is equal to 2 pi times m, some multiple, m is an integer. M is an integer. Okay. So, which means 2 pi by omega naught must be equal to n by m, and this has to be a rational function where n and m are integers. Okay, very interesting. It is not guaranteed that every sinusoid is periodic. It is only periodic if 2 pi by omega naught is your discrete time frequency. If you take 2 pi by omega naught and you can write it as n over m, some rational form, then it is periodic. Okay, so let us see if we can quickly apply this in a few examples. So, the first example that we have is x1 of n is equal to cosine pi by 4 n. Okay. What is omega naught? Omega naught is pi by 4. Now, what is the condition? Condition for periodicity? Condition for periodicity. 2 pi by omega naught must be equal to n over m. N is the period, n will be the period. So, if you find an integer value of n which satisfies this equation, m can be any integer, that is the condition. So, omega naught by 2 pi will be 2 pi divided by pi by 4. What is that equal to? 8 by 1 is equal to n by m. M can be any integer, you can choose m to be any value, choose m equal to 1, then n equal to 8. Okay. So, this function is a periodic function with period equal to 8. Okay. Let us take one more quick example. x2 of n, I am sure you should be able to do it very quickly. Cosine 3 pi by 8 times n. Okay, apply the same formula, 2 pi, so the omega naught is equal to 3 pi by 8, omega naught, 2 pi by omega naught is given by 2 pi divided by 3 pi divided by 8. So, that is 16 by 3 equal to n over m. If you choose m equal to 3, you want the smallest value of n. So, choose m equal to 3, then n equal to 16. Okay. So, this function is also periodic with period equal to 16, with period equal to 16. Okay. So, this is our understanding. Now, 3 pi by 8, 3 pi by 8 if you simplify is nothing but 0.375 value pi n. Okay. Or if you take pi by 4, this is nothing but 0.25 pi. Okay, and 0.25 pi is approximately 0.7854 is the value, 0.25 pi, the 3.17 divided by 4. Okay, so this sinusoid was periodic. Okay, this particular value of frequency was periodic. This value of sinusoid was periodic. Okay, now look at the following expression, x3 of n is equal to cosine 0.785 n. Cosine of point, look at these two values. Okay, cosine pi by 4 n will be 0.7854 n. This is only 0.785 n. Okay, what is the test for periodicity? 2 pi by omega naught is 0.785. Can it be represented as n over m? Pi is a irrational number. So, you can, as long as you have an expression for pi on one side, you will never get it to be a rational form. So, there is no value of m for which n will be an integer, for which n is an integer. So, which then says this frequency, though it is very close to a periodic frequency, this signal does not satisfy the condition for a periodic function, not periodic. Okay. So, see how different it is. In a continuous time signal, all sinusoids are periodic in frequency. There is no periodicity in the periodic in time, no periodicity in frequency. It goes from 0 to infinity. On the other hand, in discrete time signals, all discrete time sinusoids are periodic in frequency. They have a period equal to 2 pi, but not guaranteed to be periodic in time, because they are periodic only if you satisfy this condition, which is 2 pi by omega naught is equal to n over m. So, let me highlight this. This is an important condition. Anytime you are given a sinusoidal function and you have to test whether it is periodic or not, this is the simple test that you should do to apply the signals that are present. Okay, my last point that I would like to cover in this session is a question on the aspect on the Fourier representation. Okay, now in the signals and systems course, you have done a lot of study on representation of the Fourier transform and Fourier series representation of signals. Now, what you write down in the Fourier series expression is a expression of the signal, the time domain signal, in terms of the fundamental frequency and sinusoids of all the harmonics. Now, if you have a discrete time signal and you want to do the Fourier series representation, discrete time signal. Okay, and we say that this is a periodic signal with period equal to n. With period equal to n. Okay, that means you are satisfying the period omega naught n is equal to some multiple 2 pi times k. Right? This is basically the same expression that we have, or I think we wrote it with the m here. Okay, 2 pi m, or in other words, 2 pi by omega naught is equal to n over n over m, correct, n times omega naught is 2 pi. This can be also written as omega naught is equal to 2 pi by n into k. Now, the question that arises is, if I want a Fourier series representation, I want to know what are how many harmonics are present that I can obtain. Now, if you take omega naught as 2 pi by n times k equal to 1 is a sinusoid, 2 pi by n. K equal to 2 is a sinusoid, 3 is a sinusoid, you can, and similarly k equal to 0 is also, it's a constant value, but you can treat it as a sinusoid of 0 frequency. So, starting from k equal to 0, 1, 2, 3, you can go all the way, you can go only up to n minus 1, because at k equal to n, you will come back to the original frequency, because remember that's the periodic behavior. So, how many distinct sinusoids do we have for a discrete time signal that is periodic with period equal to n? The total number of periodic sequences, the number of periodic sequences, you can maybe even classify it as sinusoidal sequences that with period equal to n, with period equal to n is equal to n. K equal to 0, 1, 2, all the way up to n minus 1. There are a total of n sequences that you can find, okay, or n sinusoids. So, any signal in the discrete time representation can be represented in the Fourier domain, not with an infinite number of sequences, coefficients. All you need is n coefficients, because n is basically corresponds to the period of the signal. It is also the number of distinct sinusoids that you will have with the which will satisfy the period equal to n. So, again, this is an important result which will come when we want to look at the Fourier series representation. So, with that, we will conclude today's discussion.